Hello students, in this video we'll discuss how to find the parametrized and symmetric versions of a line. Let's be given 2 points, A and B, in R3. So what we can do is we can plot these points in R3. Here's the point A. Here's the point B. And then what I'd like to do is I'd like to find the line between these 2 points. So we're going to draw the straight line between those 2 points. And we're also going to put the origin into this problem. So here's our origin, which is a 0 vector. And then if we draw the vector from the origin to the point A, I'm going to call that vector A. If I draw the vector from the origin to B, I'll call that vector B. And then we'll consider a point on this line. So I'll draw a vector from the origin to a point on this line. It could be over here, or it could be maybe over here, or it could be over here. It can be any sort of point on that line. But in general, it has this form. And so now we notice, so we can look at 2 vectors over here. Let's call this vector over here vector R. And now if I look at this portion, this vector over here, that first vector, this vector over here is exactly R minus A. And if we look at this vector over here is the vector R, B minus R. And so what this tells us is this tells us that R minus A, from this picture, we see that R minus A is a multiple, is in the same direction, so it's a multiple of, I'll put a multiple T, it's just a scalar. That's a scalar parameter. T, B minus R. And what this does is this gives us the parameterized version of a line. So R is a function of T, and this will be A plus TB minus TR of T. And this will tell me that 1 plus TR of T is equal to A plus TB. In solving for R of T, we have R of T is equal to 1 over 1 plus T A plus T over 1 plus T B. So we can write the equation of line in either this form or in the form, we can rewrite this. So this is the parameterized version of a line. We can also use different parameters and write this in a slightly different way. So let's think about different cases over here. So let's first consider the case when T is equal to 0. So if T is equal to 0, then R of 0 will be 1 over 1 plus 0, which would be a 1. So that'll be just an A. And if T is equal to 0, we'll have a 0 over 1. So that'll be a 0. So R of 0 is equal to A. Now we can plug in a different point. If we plug in the point T equals 1, for example, if T equals 1, then R of 1 will be 1/2 of A plus 1/2 of B. And this would be the midpoint. And now let's see what happens as T gets closer to infinity. As T approaches infinity, R of T will approach, this term over here will approach 0, and this term over here will approach 1, and so we'll just get R of T will approach the vector B. So what we've done over here is we've parameterized every point in between A and B, with A being the origin and B in some sense being close to infinity. Now, of course, what we can do is we can reparameterize this with a different parameter. We can also say that the equation of a line is R, alternatively, we can write L of T, which is 1 minus t a plus t times b. And now, in this parameterization, L of 0 is equal to a, and L of 1 is equal to b. Either of these representations is a valid way of parametrizing the line. We'll see when we start to discuss curves that there's many different ways to parameterize a curve, and there's a standard way to do so called arc length parameter, and we'll focus on the arc length parameter version. Now, from these parameterized versions of the line, we can find the symmetric version of the line. So we can note from these equations over here, let's take a look over at this basic equation. So let's look at this equation over here. So L of t is equal to, we can also write this as a plus t b minus a. And this tells me that the x-coordinate of this vector will be a1 plus t b1 minus a1. The y component of this vector will be a2 plus t b2 minus a2. And the z component of this vector will be a3 plus t b3 minus a3. Sometimes we'll call this vector b minus a v for the direction, and we can simplify this. This first one will be a1 plus t v1. This will be a2 plus t v2. And this last thing will be a3 plus t v3. Solving each of these equations for t, we see that t is equal to x minus a1 over v1. We see that t is also equal to y minus a2 over v2. And we see that t is equal to z minus a3 over v3. And since all those things are equal to t, we can find the symmetric form of the line, which is x minus a1 over v1 is equal to y minus a2 over v2 is equal to z minus a3 over v3. And this is the symmetric form of the line. Thank you very much.